This is part 10, Distillation of the series, AI for Everyone. Now that we have explored the impact of quantization, we will delve deeper into distillation as another compression technique which compresses a large model into a smaller one by reducing parameter count size like 40 billion to 8 billion, which is different than reducing data type size, while ensuring that the smaller model retains most of the capabilities and knowledge of the larger model. This method provides a different perspective on model efficiency and performance retention, allowing AI engineers to optimize models beyond traditional quantization techniques. In 2015, Distillbert, a student model, was trained from BERT, a teacher model. Distillbert is 40% smaller than BERT teacher model, yet retains 97% capabilities of teacher models, and because of its smaller size, it can run 60% faster when compared to BERT model. Advantage of using distillation is that we can modify the architecture of student model to be different from teacher model. You get the biggest gain possible in speed because your student model is smaller and can run much faster at the same time while retaining maximum knowledge from teacher. Provided you have the same data you use to train the teacher model, it is your opportunity to transfer all the knowledge from teacher model to student model. And the challenge is, we need to set up training data. Also, we need to run the teacher model while student model is being trained. Cost of running both model will be high, running teacher in inference mode and at the same time running student in training mode. Remember, AI is as good as the data it was trained on. If you have bad quality or incorrect data, your AI will not be good. So how does distillation work? Here we train the student's prediction to match those of the teachers. This process of transferring knowledge from a teacher to a student in a simpler way is called knowledge distillation in artificial intelligence. In knowledge distillation, ground truth labels from training data are augmented by soft probabilities or logits distribution from teacher model and is passed to student while training. The aim of student model is to mimic the probabilities of the teacher model. As we saw in the transformer model in previous video, the temperature controls the probabilities assigned to the output. Lower temperature assigns probabilities to few output, but higher value of T will assign probabilities to much more set of output, which reveals learning pattern of teacher model. So setting of temperature greater than 1 assigns probabilities to more of the outputs. How does knowledge distillation works? 1. First, we adjust the temperature of teacher model to be greater than 1, and if needed, also in higher value for sampling. 2. We input the same statement to both teacher and student model so that we can compare their output. Student model will perform its own prediction, and teacher model will do its own predictions. 3. Student's loss will be computed using the traditional method known as cross-entropy, and we will call it L, CE, or loss using cross-entropy. In the diagram, it is shown as loss 2, hard target. 4. A special formula known as divergence of knowledge loss, or DKL of P, Q, measures the difference between the teacher's knowledge, which is P, and student's guess, which is Q. Here PI for given input of X, which is the probabilistic output by teacher model for class of I, and QI for the given input of X, which is the probabilistic output by the student model for class I. Then obtaining log of P, I of X divided by Q, I of X means how different the student's prediction, Q, is from teacher's prediction, P. If P of X equals Q of X on all predicted probabilities, that means KL or knowledge divergence is 0, meaning the student has perfectly learned. Then we do summation of KL divergence over all possible outcomes to obtain loss 1, soft target. 6. Once we have both this values, LCE, which is direct prediction of student, and LKD, which is difference between teacher and student prediction, a final loss value is calculated using formula alpha multiplied by LKD plus 1 minus alpha multiplied to the LCE loss. This final loss value is then used by student in its backpropagation to update its weights and biases. Note, value of alpha can range between 0 to 1. You might think that since we already have loss value from teacher model, why not just use that? Why even bother about doing forward pass for student model? Here is why we do that. First, the teacher model might have billions of parameters, while student might have very less number of parameters compared to teacher. So we cannot use them directly, but instead we use formula to find delta and then use this delta value in student backpropagation. Since students need a different set of loss values, we need the formula that helps find the delta of loss. Also, since we need to find delta, it implies we need two values and we can't get loss value for student unless we obtain predicted value to compare with ground truth. Therefore, we need forward pass prediction by student model. Now, the next challenge is what data to train on. This can greatly affect student model if it is not trained on right quality and diversity of data. Remember, your student model will always be capped by the teacher's knowledge. Here are some of the options related to training data. A. Using the original training data. If the original data set is available, we can pass the same data that trained the teacher model through both the teacher and the student. The teacher provides soft labels, probability distributions, and the student learns from them. Pros. Best case scenario because the teacher has already learned patterns from this data. Cons. If the data set is large, it may be computationally expensive to use it all. B. Using a smaller or filtered data set. Instead of using the full original data set, we may select only a subset of important examples. The idea is to find data points where the teacher's knowledge is most useful. For example, ambiguous cases where the teacher has nuanced probability distributions can help the student generalize better. Pros. More efficient, requires less data storage. Cons. Selecting a good subset requires additional effort. C. Using a proxy data set, synthetic or different data. Sometimes the original data set is not available due to privacy, proprietary issues, or size constraints. In such cases, we can use a different data set that is still relevant to the task. We can even generate synthetic data where we only have access to the teacher model, not the original data. Example, suppose a teacher model was trained on high-quality medical images, but that data set is unavailable. We can take a different set of medical images, run them through the teacher, and use its predictions as training labels for the student. Pros. Useful when the original data set is unavailable. Cons. The student might not learn as well if the new data set is very different. DeepSeek recently released distilled versions of the Quen and Llama models. Let's compare these distilled models with some of the most popular full-version models. The top section presents performance results from benchmark tests of well-known full-version, non-distilled models. The distilled versions are labeled with distill in their names. DeepSeek used R1 as the teacher model and distilled knowledge into various student models from the Quen and Llama families. Take note of how the 14 billion parameter distilled version of Quen compares to OpenAI's O1 Mini. Also, observe how the 32 billion parameter distilled version performs in comparison to both OpenAI's O1 Mini and its own undistilled counterpart. This demonstrates the great potential of distilled models, where knowledge from a larger teacher model is transferred into a smaller student model while maintaining comparable performance. At first glance, model distillation might resemble fine-tuning, which we will cover in the next video. However, there is a key difference. In fine-tuning, there is no teacher model. Instead, new data is used to retrain the model. Since we've mentioned DeepSeek, let's discuss their approach and how they managed to outperform industry leaders. The initial phase of LLM evolution focused on proving that the technology was viable for both industry applications and everyday use. It's not that optimization techniques were overlooked. Concepts like quantization and distillation had already been explored in research and published findings. However, outside of research labs, few pursued optimization as a primary goal. DeepSeek faced constraints that made optimization a necessity. Necessity, after all, is the mother of invention. They took a proactive approach by implementing multiple optimization techniques in combination, as outlined below. DeepSeek implemented several key optimization techniques to enhance efficiency and performance. FP8 Mixed Precision Training. Instead of the commonly used FP16 for training, DeepSeek adopted an FP8 Mixed Precision Training framework. It's important to note that FP8 is not the same as NT8, which only supports integer values. FP8 still uses floating point representation. To prevent accuracy loss, they periodically copied results to FP32, overcoming the limitations of lower precision. Mixture of experts, MOE, architecture. DeepSeek utilized the MOE architecture to reduce computational costs and accelerate performance. Implementing MOE is complex, but they successfully integrated it. Thanks to this architecture, only 37 billion parameters are activated out of the total 671 billion, significantly cutting down on computation. Multi-head latent attention, MLA. MLA addressed KV cache storage limitations, allowing DeepSeek to reduce KV cache usage by an impressive 93%. Multi-token prediction, MTP. This technique enables the model to generate multiple tokens per step, improving data efficiency and accelerating learning. It also enhances planning efficiency by allowing more feedback per iteration. Reinforcement learning, RL, and AI feedback. Unlike traditional RLHF, reinforcement learning with human feedback, which relies on human reviewers, a slow and costly process, DeepSeek used RLAIF, reinforcement learning with AI feedback. During inference, they employed group relative policy optimization, which enables the model to recognize its mistakes and backtrack to correct them. By removing RLHF, DeepSeek significantly reduced training costs and increased training speed. Hi, I'm Naunihal Singh Sidhu, a Microsoft-certified Azure Solutions Architect with over 25 years of experience in IT, specializing in AI-driven transformation, enterprise architecture, big data solutions, and digital innovation.